Hello and welcome again to my Physics Online video lecture series. In today's video we're going to be talking about another application of the Lorentz force, which is the mass spectrometer. So this is a continuation of our series of discussions about the motion of a charged particle in the presence of an electric and or magnetic field, mostly in this case magnetic fields. You may from our previous discussions recall that we have introduced a couple of things. One is the velocity selector. So the velocity selector has the ability to sort of select what velocity of particles will make it through the selector. And that velocity, that particle speed, is E divided by B, assuming that everything is oriented perpendicularly to each other. There's also, of course, a sine of theta term if they are not so oriented, but generally they are perpendicular. Number two was motion of a charged and massive particle in a magnetic field. And for that one, we tended to have circular motion or helical motion, and the radius that these particles would undergo was basically the momentum, m times v, divided by the charge times the magnetic field. And sometimes maybe we would make this m times v perpendicular, the perpendicular component of the velocity to the field. For today's video, again, however, we're going to assume a perpendicular magnetic field. So how does a mass spectrometer or charge to mass spectrometer work? Well, basically what we do for that is we build a velocity selector to control the incident particle's speed. So we'll just call this selector V selector. We already know how that works from a previous video. And then in this other region, there is a magnetic field B, which may be into the board or screen or out of the board or screen, etc. Now our particle has some charge to it, and it enters into this uniform magnetic field with the velocity selected by the velocity selector. So when that happens, we end up with a force on the particle, QV cross B, which is to the left for a positive particle. And that force basically will cause the particle to undergo a sort of circular motion. So if this is a positively charged particle, then we get this motion. If for some reason we have a negatively charged particle entering here instead, so I'll draw a negative charge in purple. Also with the same velocity vector v, then it will undergo a circular motion off in the other direction. Now, usually what happens to make this work out is that we have a detector array somewhere. For example, it could be along this wall right here. All right, so maybe this wall fluoresces when particles crash into it. And then usually there's some sort of a detector that's watching for fluorescing. So maybe it's like a camera, for example, that can take a picture that, oh, there's a bright flash occurring right here, for example. And that is then sort of noted as a particular position. If this is the entry to the chamber and this is where we're getting collisions, this distance right here is 2 times the radius from this page. Okay, so 2 times the radius. So we would be able to write that 2r is 2 times mv over qb. All right, and that means that m over Q, the mass over charge ratio, is going to be B times R divided by V. And so this gets us the mass to charge ratio, or sometimes it's flipped the other way around and we want to get charge to mass ratio, either way. And this lets us measure what is the relative mass and charge of a given particle. So that's a cool application of magnetic field. As an example, let's say that we happen to have a proton. Maybe we have like a hydrogen atom that we've stripped the electron off of, for example. And it passes through a velocity detector with a speed of 4 times 10 to the 6 meters per second and enters into a spectrometer of field strength 0.12 Tesla. So we want to know how far from the opening does this proton collide. And the fact that it's a proton tells us what both the mass and the charge is. See, the mass of a proton is approximately 1.67 times 10 to the minus 27 kilograms, and the charge is approximately 1.607 times 10 to the minus 19 coulombs. This right here, of course, is the speed. This right here is the magnetic field strength, and this term right here, the how far from, is equal to twice the radius. So we're basically using this first equation. Okay, so we should be able to write that the distance, which is equal to 2r, is 2 mv over qb. So that's 2 times the mass, which is 1.67 times 10 to the negative 27 meters per second, kilograms, times the speed, which is 4 times 10 to the 6 meters per second, divided by the charge, which is 1.607 times 10 to the minus 19 coulombs, times the field strength, which is 0.12 Teslas. Now this is something that you might want to plug into your calculator to solve. So we do that. We go 2 times 1.67 divided by 1.607 divided by 0.12. That would give us 69.28. And then we got the other powers of 10. So this is we'll call it 6.9 times 10. So I said 69, so that's 6.9 times 10 to the 1 minus 27. So 1 minus 27 gives me negative 26, plus 6 gives me negative 20, minus 19, divided by minus 19 gives me negative 1. So this is the distance in meters. So we're looking at about 69 centimeters. So that's where this proton should be colliding with the wall of the chamber under these conditions. Okay, so that's particle, particle mass over charge spectrometry in a nutshell. It can be done with individual protons and whatnot. It could also be done with larger molecules, with like actual molecules. Although the method often used by chemists now for measuring the mass to charge ratio in molecules is slightly different than what's been described here. We still use this method as described or something like it in fields like plasma physics, where we're often looking at electrons or protons, that kind of thing, individual plasma, essentially ionized atoms or electrons. For larger molecules, they use a more complicated system that is basically a sort of filter in which they apply two fields. And the two fields, one is at a high frequency and the other is at a low frequency. And essentially a mass over charge that is larger than a certain number will tend to be deflected out because of the high frequency, and smaller will tend to be deflected out because of the low frequency. And so essentially they just tune these two frequencies until the atoms don't get reflected out, and then usually is actually a molecule, then that's what the mass of that molecule is. But that's kind of beyond the scope of today's video lecture. I'm mostly just including it for the sake of completeness. So that's a relatively short lecture for today, but that's all that I've got for today's video. Hopefully you learned something, and thanks for watching.